What's up, everybody, and welcome back to another video on SAT Math, and this one is part 3 of a 4-part series involving all of the critical concepts that you need to know to nail the math section of the SAT. And this one is all about problem solving and data analysis. So without further ado, let's get into it. The biggest subcategory within this section has to be, without a doubt, ratios, rates, and proportions. I've done the analysis. I see these problems probably more than any other problem type on the test, so it's very important that we understand the core concepts herein. First, let's talk about ratios. Now, ratios are really the same thing as a fraction. That's all it is. It's a comparison between two numbers. In addition to writing a ratio in fraction form, we can also write it in this type of form where it's 1 to 2. So 1/2 is akin to a 1 to 2 ratio, or we could also say, for example, 4/9, again, in that 4 to 9 ratio. 2 to 5 or 2/5 is like a 2 to 5 ratio, and of course 3/7 is like a 3 to 7 ratio. So a lot of times too, when they're asking you, hey, you need to find the ratio of A to B, a great way to do that is actually put it in fractional form of A over B when you're trying to isolate that particular ratio. So now we're going to walk through a quick example where they say, hey, what is the ratio of A to B? So for example, we start with an equation and we've got 3A equals 7B. Now I know a lot of you want to immediately jump to say, well, if they're asking for the ratio and it right now says 3A equals 7B, the ratio is 3 to 7. But you can't go that quickly. First, you gotta think, all right, well, if I want the ratio of A to B, again, I wanna put it in fractional form of A over B. So what we do is we divide both sides by 3, right? We cancel out those 3's. Now we have A equals 7B over 3. Okay, in the next step, we wanna get A over B. So now we're going to divide both sides by B. And again, canceling out the B's on the right side. And now we've got A over B is 7/3, which means that my ratio of A to B is simply 7 to 3. Next, let's talk about rates. So what are rates? Rates are essentially, from this equation, distance equals rate times time. And we're basically talking about speed. This equation, I know you guys might think it's super simple and I don't need to worry about it, but it's such an amazing tool, at least I find when I'm working through problems, to have this as a backbone. So when I'm trying to figure out, hey, do I need to know time? Do I need to know rate? How do I get those? I just plug it into this formula and I don't have to overthink it. So again, in this formula, let's just go through the terms. D equals distance, R equals rate, again, which is synonymous with speed, and last but not least, T stands for time. Now let's look at a particular example involving rates. So if we look at this problem, it says Laura can swim 2 laps in the local swimming pool every 1.5 minutes. At this rate, how many minutes does Laura need to swim 12 laps? Bearing in mind that we've got distance equals rate times time. Now notice I color-coded those numbers, right? The numbers in blue correspond to distance and the number in green corresponds to time. All right, so now how do we break it down? So first of all, with the initial pieces of information, I can actually calculate that rate. So I'm gonna go ahead and do that, and I'm gonna plug that in as follows. It's gonna say 2 equals rate, which is unknown, times 1.5 minutes, okay? And then I'm gonna isolate R by dividing both sides by 1.5. By 1.5. And what do I get? I get R equals, instead of 2 over 1.5, I'm going to double it, double numerator and denominator, so I don't have a decimal in a fraction. And I've got a rate of 4/3. All right, now I can plug this in again with this information. How long does Laura need to swim 12 laps? So now I've got 12 equals a rate of 4/3 times an unknown time. Okay, now we can solve this way. So I'm going to isolate by multiplying both sides by the reciprocal of 4/3, which is 3/4, like so. That cancels. 3/4 of 12 ends up being 9. Now this isn't the only way, by the way, that we can solve this problem. Instead, we could have used a proportion. So for example, I could have said, if we do 2 laps in 1.5 minutes, how long will it take for 12 laps? And again, the time goes on the bottom, right? We have matching time and matching laps on the top. This is my unknown time, and now we can just cross multiply, right? So 12 times 1.5 ends up being 18 equals 2x. Dividing by 2 gets us that exact same answer of 9. Next, let's talk about proportions. So proportions are incredibly important on this test, and as you saw in the last example, even though I did solve it using distance equals rate times time initially, proportions came in quite handy there as well. When we talk about proportions, all right, it's essentially a fraction equals a fraction. That's how you want to think about it, and this is sort of a standard way to look at it. A over B equals C over D, or if we're talking ratios, A to B is the same as C to D. Now, when we solve a proportion, we always want to cross multiply. That literally means the variables are crisscrossing, jumping across the equal sign to multiply each other. And when they do jump across, you have a nice simpler equation of B times C. So you see how the C jumps down to the B? It's B times C equals A times D. So if we put this into practice, let's say we're given a proportion as such, or you set up a proportion like we did in the last example. All we do to solve is cross multiply, right? So the 1 multiplies the 9 and the x multiplies the 3. And now we have a new equation of 3x equals 1 times 9. So to simplify, we have 3x equals 9, and of course this gives us x equals 3. Continuing on with an example for proportions, let's take this example. We said if 7 pounds of plums makes 8 fruit rolls, how many pounds is needed to make 20 fruit rolls? The first thing you want to do before you set up a proportion is set up your categories. So now we're talking about pounds of plums and corresponding fruit rolls. So we want to sort of break down those categories, and it's arbitrary. I could have put rolls on top. I ended up putting plums on top. It's just arbitrary. So now we've made that. Now we get our framework for the proportion, right? Because we know it's going to be a fraction equals a fraction. Well, I know on the left side, I've got 7 pounds of plums to make 8 fruit rolls. So you notice how those two are together, they're paired up. And on the other side, we need to make 20 fruit rolls, but I don't know the amount of plums we need. That's why there's an X in that position. All right, to solve for this, we again cross multiply. So then the X jumps down and the 7 jumps across and down, and we get 8X equals 7 times 20, which is of course 140. Last but not least, we divide both sides by 8, and I get X equals 17.5. So the answer is it takes 17.5 plums or pounds of plums to make those 20 fruit rolls. Now we'll jump into another example. Here it says to make 4 batches of cupcakes requires 7 tablespoons of sugar. How many tablespoons is required for 5 batches? All right, so let's check it out. We again set up our framework. We've got batches on top, tablespoons on the bottom, and there's our baseline structure. So we see that we've got 4 batches for those and requires 7 tablespoons of sugar. Now we need to make 5 batches, but we have the tablespoons is unknown. All we gotta do now is cross multiply, boom, and we get 5 times 7 is 35 equals 4x. Last but not least, isolate by dividing by 4. Boom, cross those out, and we get x equals 8.75. So it's 8.75 tablespoons of sugar. Now we're gonna talk about percents. This is such an important category on the SAT. And whenever we talk about percents, I always go back to what my French teacher told me in high school, which is percent is a French word and it translates directly, or well, the right way to say it is %. And that cent part, okay, that separated cent part translates directly to 100. So really, we're saying percent, we're talking per 100. So that's a very important thing to remember when we're trying to understand percents. So like for example, when we say 9%, we're really saying 9 per 100. So it's really 9 out of 100, okay, 9 hundredths. And if we wanted to write that in decimal format, it's simply 0.09. Again, that 9 goes in the hundredth spot. Another quick way to think about that when we go from percent to decimal is we're moving the decimal 2 spots to the left, but we're going to talk more about that in a second. Likewise, 73% is simply 73 per 100, or 73 hundredths. In decimal format, once again, 0.73. 16% would be 16 hundredths or 0.16. And then when we get to numbers bigger than 100, we still move the decimal only twice. So it's 125 hundredths, which translates to 1.25. When we solve for percents, I like to use something called the percent equation. This is what I highly recommend, especially for the SAT level type of math. The percent equation is very simple. Percent times whatever the total is gives me the part. The only thing you remember is the percent goes in decimal format. So like we saw before, 16% is 0.16. You'd plug in 0.16 into this equation. So when we ask a question, what is 12% of 50? And notice how it's all nicely color-coded. That 12%, that's the percent part, that's going to come down first as 12%. But again, notice where the decimal is and notice where it needs to be. It needs to be moved 2 spots to the left. All right, so now it's really 0.12. Now it's in the equation in the right format. And then we've got the total. What is 12% of 50? So 50 is coming next, and it's going to be multiplying that 0.12 to get my answer, which is of course 6, right? This is sort of like, it's the same thing as multiplying 5 times 1.2 or 0.5 times 12 if you'd like to manipulate numbers that way. So there we go. 12% of 50 is indeed 6. Another way to use the percent equation is in a question like this where it says 9 is what percent of 45? Now we're actually trying to solve for the percent, but the beautiful thing is we just use that same percent equation, decimal version of course for the percent, and we're good to go. So in this case, the unknown is the percent. It is what percent of 45, 45 is still that total, equals 9, right? All right, now we gotta figure this out simply by isolating. So how am I gonna get rid of that 45? We divide both sides by 45, cross those guys out. And x equals, as a, yes, it's 9/45, but as a decimal, it is 0.2 or 0.20, same thing, right? If I add a 0, because 1/5 in decimal format is of course 0.20. And then last but not least, to convert it to its appropriate percentage, just like before I was moving the decimal 2 spots to the left, now I move it 2 spots to the right, and the answer is 20%. So again, 9 is 20% of 45. Now here's another example using the percent equation. So again, there it is for your refreshment. It says 30 is 75% of what number? Now we're actually trying to find that total. You see the part is there and the percent is there. The total is what's missing. So let's give it a shot. So again, we've got 75% in decimal format, that's 0.75, times my total, which is unknown, equals 30. Now what do we do? Of course we isolate, so we divide both sides by 0.75, and what do we get? 30 divided by 0.75 becomes 40. So there we go. 30 is 75% of 40, and that makes sense because 75% is really 3/4. So of course 30 is indeed 3/4 of 40. Next, let's talk about percent increases. So what is a percentage increase? It means we're increasing the value by a certain percentage. So let's take a look at this example. We have a starting value for any item of $1,200, and we know that there's meant to be a 20% increase. So how are we going to calculate this precisely and efficiently? What we're gonna do is we're gonna take that 20 and we're gonna add it to 100. So anytime we've got an increase, we're gonna add that value to 100. Now, if it was a decrease, we'd be subtracting it, but we're gonna get to that in a moment. So we add those two together, we get 120%. Next, we take that decimal and we convert it by moving the decimal 2 spots to the left. Boom, boom. So now instead of 120, we have 1.2. Then we take it in decimal format, in keeping with our percent equation, and we multiply it by that starting value, 1,200, to get our final value after the 20% increase of 1,440. Now we're gonna talk about the other side. We're gonna talk about percentage decreases. So in this case, we're going to take our same starting value of $1,200, but we're gonna decrease by 35%. Now it's very important to remember, just like in the increase where we add to 100, here we are going to do the opposite and subtract from 100. So we're gonna take 100 minus 35, which gives us 65%. And that's what remains. When we're removing 35%, we have a remaining 65%. Okay, now again, just like with the percent equation before, we have to move the decimal 2 spots to the left to get the decimal equivalent, which is 0.65. All right, now we're nicely set up. We multiply this times that starting value of 1,200, and we get 780. So a 35% decrease from 1,200 takes us to 780. Next, we're gonna talk about units and unit conversions. This is a very big section on the SAT and very important to get down these basics. What do we use to convert units effectively? The answer is conversion ratios, all right? So what is a conversion ratio? Pretend they said, convert 2 miles to feet. All right, so what are we gonna do here? So first we're gonna say, all right, I've got 2 miles, I need to convert it to feet. I like to throw it over 1 just so we have it in a nice fraction format. Okay, well, to make that conversion, we've got to multiply by something that equals 1 first and foremost, because otherwise we change the value. So why did I choose that ratio? Well, because 5,280 feet actually equals 1 mile. So technically that is one we are allowed to multiply with, and it doesn't change the value. And also the fact that I've got miles on the bottom, that's very important because I want the miles to be opposite the miles in the original value. That way we can cancel those out and we'll be left with feet, thereby completing the conversion. For the ratio on the right, I've got 5,280 feet over 1 mile. And yes, I know it is singular, but I just had to keep the units looking the same. So now we are going to cancel out those units because we got miles on the top, miles on the bottom, and we are good to go. And then once we have that, we see we're left with feet. Simply multiply across. 2 times 5,280 is 10,560 feet. Now let's look at a more difficult example involving conversion ratios. So let's say it says convert 3 days to minutes. So this is going to involve a few more steps. Let's check it out. First, we start with 3 days, and I'm going to do it step by step. I'm not going to go straight to minutes. First, I know that it's easy to say we have how many hours in a day? 24 hours in a day. And notice again, the day is going on the bottom, so it's on the opposite side of the days in that first ratio. So that way they're going to be able to cancel out eventually. Then now I've taken it from days to hours. Now I can complete it by going from hours to minutes. So we have this next one where again hours has to be on the bottom and the equivalent amount of minutes, 60 minutes, is on top. Now we cross cancel those hours. And now we're in great shape. We just multiply across the top. 3 times 24 times 60 gives us 4,320 minutes, and there it is, we are done. Now let's talk about scatter plots. So scatter plots are amazing. It's a way that we use real data, plot it on a grid, and then sort of sit there and analyze, and we can maybe make predictions, make lines of best fit, etc. So they're very important. So when we talk about scatter plots, that line of best fit is one of the most commonly tested subcategories within scatter plots. All right, now let's talk about scatter plots in terms of the line of best fit, and the best way to do that is with this example. So you see here, we've got this actual SAT problem and a corresponding chart, and what they're asking us to do is to essentially analyze the line of best fit and use that analysis to answer these questions. So we're going to step through that here. This is kind of superfluous in terms of what we need to answer this question. So just take it as these are real data points. There is the line of best fit, and we'll go from there. So first it says, the profit by the end of May will be $2 million. Now this almost looks pretty good because we see that this line of best fit hits 2 million right at the end of May. So it's not a horrible choice. The problem is that definitive language. The profits by the end of May will be $2 million. That's a prediction. We don't know. Even right here, it's at 2.5 million. Maybe it shoots back up. So to make that definitive statement is going a little too far with that line of best fit. Next, we're going to look at C. So it says the profit decreases by approximately $1 million every 0.2 days. Now, you want to be careful not to look at any of the data points. They're talking about the line of best fit, so we got to stick to that. So I'd say in 0.2 days, which might be right here, it's saying it's going down by $1 million. No way. It's barely going down by maybe even $250,000. So that one's definitely out. Then let's look at D. The profit is expected to decrease by $8 million over the course of May. Well, it starts at $8 million, but the prediction is that it's expected to decrease only by $6 million as it appears. So I'd say that's out as well. So let's take it back to B. B, it says the profit decreases by approximately $1 million every 5 days. We'll check it out. We're at 8 million. Here is 5 days right there. And boom, looks like we dropped to 7 million after 5 days. So I feel pretty confident that B is going to be the right answer in this case. Another commonly tested concept in terms of lines of best fit is your ability to draw them in and interpret them. And also, not only that, but being able to distinguish whether you've got something that is linear versus non-linear. If we take this example here, we're trying to figure out which of these answer choices is what is being graphed to the right. So we're trying to say, hey, which function is a great approximation for these data points? So the first thing you want to do is draw in that line of best fit. So we're doing our best there. And does that look like a straight line? Definitely not. It's definitely some sort of a curve to it. So I'm immediately going to eliminate A and B because those look like linear functions. Next, it's down to C or D, and those are both exponential. But it looks like it's decay, it's not a exponential growth because it's coming down. In that case, the value inside cannot be something like 2 where it'd be doubling every time. It looks like it's cutting in half every time. So this C value looks like a great answer, and that's it. Next, we have key features of graphs. So I want to talk again about some of the most important features of graphs so you can answer these questions pretty easily. So when we talk about slope, we want to break that into two categories, right? So slope in this case, when it's positive, is increasing. And to give you an example, here's a chunk where it is increasing. It's going up from left to the right. And then it can also conversely be decreasing, where it's kind of going down from left to right. If you want to think about going down like a roller coaster, it looks like it's climbing up on the left side and then boom, and shooting over and going down. So that becomes a negative slope. Of course, if it's totally flat, we would have a slope of 0, and a slope straight up and down would be considered no slope or undefined. Another critical point is the y-intercept, which is always considered to be the initial value, and you see that y-intercept right there is that green dot. Another important point is the x-intercept, and the x-intercept is the point of no value. A lot of times, if you have an economic function being graphed, that's where the profit goes to 0, and it's denoted by that purple point down on the bottom. Last but not least, specifically for these quadratics, we have the vertex, and the vertex is either the minimum or the maximum point, and of course in this downward facing parabola, that would be the top of the hill, and the vertex would be the maximum as denoted by that yellow point. Something else that's very important to know is how to differentiate between linear and exponential growth or decay. So I got a little table here. One side is linear, one side is exponential, and we're going to show you the data here. So first of all, pretend we've got this data 1, 2, 3, 4, 5, 6. The y's are 3, 6, 9, 12, 15, 18. How do I know this is linear? Because it is going up by a constant amount. Something is being added to it every time. So it's going up by +3, +3, +3. And again, it's corresponding to a +1 on the left side. That's also very important. But as long as that ratio is +3 for every +1 on the x side, we know we've got a nice linear function, a nice linear equation. In contrast, for exponential, we see that as the left goes up by 1, the y is not going up by a consistent amount in terms of addition. Instead, it's going up by a multiplying factor, and in this case, it's ×2. So doubling, 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 and doubling. So that is how we could differentiate if we're looking at data, actual hard data, between linear versus exponential growth. It's also important to be able to identify graphs that are linear versus exponential, which may not be that difficult for some folks, but for folks who are unfamiliar with this distinction, linear is always a line, it's always straight, right? Straight down the middle. So this is one with a positive slope, y equals 2x minus 5. And here we got a negative slope of -0.5 or -1/2 x with that y-intercept of 4. Likewise, exponential can be positive or exponential growth, as we call it, where it's sloping up. And in this case, that is a 1.2 inside, which means it's growing by 20% every year or day, depending on whatever the time unit is. And then here we have exponential decay, and you notice now inside the parentheses, it's now a number between 0 and 1, like 0.7, 0.3, 0.1, so on and so forth. Now let's go to data inferences. This is a notoriously difficult and confusing subcategory, so I want to go over some of the main points that you need to know and understand to rock out in this section. So first of all, they talk sometimes about margin of error. What is margin of error? So let's say they say the mean or the main value that we determined is 72 with a margin of error of 5. That means that the true value of whatever you're trying to measure is within 5 of 72, so it could be +5 or -5, meaning down to 67 or up to 77. And another thing that is often talked about is confidence level. It's like, what is confidence level? Well, it's kind of what it sounds like. If you have a 99% confidence level that you've gotten the right piece of data, that's higher than 95%, higher than 80%, okay? So for example, we would call it the level of certainty that the correct value is within the margin of error of what we've measured. So it usually makes sense that if let's say my margin of error is, let's say the value is 72, and the values could go up to 100 and down to 50, something like that. If I want to have a 100% confidence level, I'd make that margin of error as wide as possible to cover everything. Now that doesn't really tell you anything, because if you have that big of a margin of error, your study is not very good, doesn't give you any insights. But the point is if our margin of error is so wide that we know every potential value is in there, our confidence level is 100%. So what that means is as the margin of error increases, the confidence level increases. As the margin of error decreases, the confidence level likewise decreases. Another thing that you gotta be comfortable with is how to make data inferences from tables. So we're gonna talk about a couple examples here. So let's say we've got this nice table of male and females enrolled in math and science at some university or school or whatever, and we've got the totals and everything listed out nicely. All right, so say we get the question, what fraction of students surveyed take math? Okay, we know that the total amount of people that take math is 70, right? We know that the total amount of students, period, we're talking about the total students, is that 70 and that 130. Okay, so that's how we read this table. It's not just 70, that's the people that take math, but the total amount of students is the combined value of that 70 and 130, which is of course 70 over 200. Now we're gonna get that same data set, but we're gonna ask a slightly more complex question. Of the females surveyed, what fraction of students surveyed take science? Now this is a sneaky question because now they're not just asking about everybody. They say, when you gotta look at of the females surveyed, immediately now we're limiting the survey to simply female. So you notice how that's now highlighted. Of the females surveyed, what fraction of students surveyed take science? Well, what is that? It looks like it's 58 take science out of, now it's not the grand total of 200 because we've limited it. We've cut our group, our initial pool to just the females. So then that total is 46 and 58. Add those together and we get a fraction of 58 out of 104. One more quick example with this same set of data. Of the students who like math, what fraction of students surveyed are male? All right, now again, we're limiting it to students who like math. So that is this subsection, of course, assuming they're not just taking it, but they also like it, right? What fraction of students surveyed are male, all right? Well, we again know that it looks like there's 24 male out of a total of 70 that take math, and that's it. Now let's move on to center, spread, and shape of distributions. So there's a lot of information to unpack in this category, very important category. So first of all, we are always assuming that we're analyzing some sort of set of data. So here's a sample set of data, okay? And this is the entire thing, and that red's gonna come in handy where we're gonna talk about mean, all right? So first thing you gotta know is, what is mean? Mean is synonymous with the word average. How do we take an average? We take that entire group of data, all those numbers, we add them together and we divide by 13. Why? Because there are 13 numbers in this data set if you count them up, and then we sum it up, divide, and we get a mean of 5. All right, next you also need to know, what is the mode? The mode value is the value that you see the most frequently. So mode kind of sounds like most, so you can use that to help yourself remember what mode is. And again, in green, I've highlighted the mode, which is 3. Now, it's not the most, it's not the biggest value, it's not 9, it's the one you see the most. Therefore, the mode, the value you see the most frequently, is of course 3. Next, we have the median. Median sounds like middle, and it is indeed the middle value of the set. Now, to find the median, the first thing you have to do is organize all the data from least to greatest, and then you look at that precise middle value. And in this case, because we have an odd number of values, it is the 13th value, which is 4. In the case you have an even set of data, let's say we had 12 pieces of data, you'd have 2 values kind of in the middle, right? You'd have the 6th value and the 7th value. In that particular case, you take the average of those two, meaning if I had my 2 values being 4 and 5, I'd add 4 and 5 together, divide by 2, and I get 4.5. The other way to think about it is, what's right between 4 and 5 is 4.5. Last but not least, we have the range. Range is simply the greatest value minus the least value. Those are denoted in purple, right? So 9 minus 1 gives us a range of 8. Next, we're going to talk about standard deviation. Believe it or not, this is tested on the test, but the great news is you don't have to ever calculate it, you just have to understand what it means. So standard deviation is the measure of the spread of the data. So what do I mean? We're going to take 2 examples where we have a larger standard deviation and a smaller standard deviation. So here's a large standard deviation. You can see from the data, it's really spread out, right? 2 5s, 2 6s, 2 7s, 2 8s, 2 9s. And now in a smaller standard deviation, 6s and 7s, it's the same amount of data, but it's all bunched closer together, right? They're really close. It's really sixes or sevens, maybe the mean is 6.5. And now what does the graph look like of the larger standard deviation? Look at that nice even spread across the 5, 6, 7, 8, 9. It's very equally distributed versus here, it's all bunched together at 6 and 7. So again, standard deviation is that spread. When it's a smaller spread, it's a smaller standard deviation, and vice versa. When it's more spread out, it's a larger standard deviation. Something else you should get familiar with is box and whisker plots. And the reason why is, look, I've seen them on real tests before. They don't show up very often, but I saw like a 3-part question on box and whisker plot once. So I do think it's worthwhile to know how to use these, and it's not that complicated, so I'm gonna explain all the ins and outs right now. This is what a box and whisker plot looks like. The data is at the bottom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and there's some key parts. So first we've got the left edge in red, which denotes the minimum, and in this case, the minimum value would be 2. Then of course we've got that right edge, and that's like, these are the whiskers of course, and that is the maximum value. So if you know those 2 points, you can calculate the range, which in this case is 8. Then we got the middle value down the line, down the middle right there at 6. And again, it doesn't have to be in the middle of the box, it just happens to be here. That gives us the median. So if they ever ask you what's the median in a box and whisker plot, is where that line is. Then we have this orange edge to the left of the box. That is what's called the lower quartile, and there it's at 4. And last but not least, we have this green line here, which is the upper quartile. Now, you likely won't need to calculate the lower quartile and upper quartile from a set of data, but if you do, the lower quartile is the median of the bottom half of the data. The upper quartile is the median of the upper half of the data. So I'm just telling you that so you know what those terms are, but I can almost guarantee that's probably not going to be something you'll need to calculate. Finally, we're going to end on data collection and conclusions, talking about data collection. And again, this can be a really tough category for a lot of people. So let's talk about the main methods that we can use. We can use an observational study, and that is where you observe subjects and record data based on an existing factor, usually with no interference. So sort of like you're going out and observing animals in the wild. This is where an observational study would make a lot of sense. You might also have a controlled experiment where you test a single variable using 2 groups, a control and an experimental group. This might be something you would use if you're testing a pharmaceutical, right? You want to see if it works. So you say, hey, you guys are the control group, you take no medication. You guys are the experimental, you'll take this new drug, and we're going to compare and contrast after 2-3 months, something like that. Finally, you could give people a survey where you gather data via questionnaires. You say, hey, on a scale of 1 to 10, what's your thoughts on building this new highway through our town? Something along those lines. Now, understanding those is great, but you don't need to necessarily know those in particular. But what you want to be careful of is when we're thinking about how to collect and sample data, we want to look out for inherent biases. That's the key. That's what they're always trying to test you on this test. The biases can come in these 4 broad categories, and they're not going to make total sense yet until I show you examples. But it could be in the location of where these surveys or experiments are happening. It could be based on the preferences of the people that they are selecting or sampling for these studies. It can be the types, meaning the types of people or even the types of products that they're looking at. If they're making these random pre-selections of groups of people or items, that can include a bias. And then of course, if you're selecting people or things based on a certain outcome, that will of course introduce biases as well. But let's talk about particular examples. So we've got an example from an actual SAT problem. It says a school district wants to conduct a sample survey to determine the average number of sports played by high school seniors. Which of the following survey methods is most likely to produce valid results? So it says the district surveys 500 randomly selected high school seniors in the district who play baseball. So I like the word random in there, but if we're trying to talk about people who play sports, the problem with this is you are inherently biasing towards people who have a preference for athletics because you're selecting people who play baseball. So that's an example of an incorrect bias that's being injected by way of sampling. What about option B? The district surveys every 10th student who enter the football stadium at the district championship game. So to me, this is a problem with the location of where you're doing it, right? If you're doing it by the football stadium, I believe there's a greater likelihood that these people like sports. They're more likely to play sports if they're going into the football stadium. If we look at option D, the district selects one high school in the district and surveys all of its students. Now, this doesn't sound like it's got a bias, but if we want to get a nice even sampling of the district, why focus on one school? We should take a sampling from the district. So this is again another location bias, which is not totally clear how it's going to bias the results. It's just not the best answer. And that leads us to C, which is said the district surveys 500 randomly selected high school seniors in the district. It's perfect. It's across the whole district. That's the ideal sample space, and we're good to go. So again, we've got these possible biases, and we're going to go through one more example just to continue to clarify. A local package delivery service wants to improve the efficiency of its deliveries. As a first step, the management team decides to conduct a study to determine the average length of time from the arrival of a package at the company's mail center until its delivery at home. Which of the following methods is most likely to produce valid results? So first it says the team selects the 1,000 heaviest packages in a 1-week non-holiday period and records how long it takes for each package to reach its destination. Why select the 1,000 heaviest? That doesn't make sense. Now we're biasing by types of packages. Because maybe heavier packages take longer, maybe they don't, maybe they're delivered faster, but whatever is the case, you're introducing some bias that's going to skew the results. Next, with option B, it says the team calls 1,000 residents in their delivery area and asks them whether they have received a package from their service in the past week. They will then record how long it took for those packages to reach their destination. So the problem with this is now you're biasing by outcome. So you're calling people first and saying, hey, did you receive it in the last week? And then if you did, you're gonna record how long it took. Well, wait a minute, what if they haven't received it yet? Now they're out of the study. So that's an outcome that you're using to make your sampling, and that's gonna bias the results. That last one, the team selects a random sample of 1,000 packages arriving at the center over a 1-week non-holiday period, records how long it takes for each package to reach its destination. Perfect, pure, simple, no biases, and we're good to go. I hope you found this presentation useful, and to everybody taking their SAT soon, I wish you all the very best of luck. And if you did like this video, please click that like button and make sure to click subscribe if you want to see more from the Scalar Learning channel. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.